Hi everyone, this video will take us through the Simple Harmonic Motion Lab, particularly the analysis for day 3, in which we investigated period versus amplitude, the analysis for day 4, where we investigated the relationship between period and the spring constant, and then we'll just wrap up the entire lab with some thoughts for moving into the next set of material. In day 3, we investigated period versus amplitude. Now, if we want to find or isolate the effect of just this variable, then we need to hold constant the other things that might affect period. So you were assigned a specific value of spring constant and mass. If you didn't use those, you would likely have chosen a different constant value, and you would have discovered a similar relationship, but your actual value of period might be different. So we went through and changed amplitude here. Now there was the option to choose amplitude anywhere from 1 to 10 centimeters, so that was selected by you if you did them all or just a handful of 6. It's whatever you wanted to choose. And what I wanted to include here is the basic finding. This is the amplitude when this is the period when the amplitude was 1 centimeter, and this is the period when the amplitude was 8 centimeters. And these two have a very different amplitude, but a very similar period. And we can see that in each of these situations, the crests are at the same time. And so that was the big finding for us, was that as we changed the amplitude, the period was unaffected. Here's that data in the quick graph program, and I just wanted to go through a couple things that people may have found. So this is the period versus amplitude data. When we take the curve fit data, we got 2 different answers. A few people put linear, and if you actually chose this in the analysis questions, it's not like you're wrong. It's linear in a certain way. And what we're basically saying with this model is that the slope is 0 and that's the intercept. But linear sort of implies that this variable has an effect on this variable. In this case, it doesn't. And so what we preferred to see in this situation was that there was no relationship between the variable. In other words, whatever the period is, it was affected by other things, and that amplitude was not that thing. So this is the graph. This is all the representations shown together, and we see that in the experiments that investigated the relationship between period and amplitude, there is no relationship between those variables. In other words, amplitude has no effect on period. Surprising result. In the next experiment, day 4, we investigated the relationship between period and spring constant. Just like we did in the past, we held some things constant. So if spring constant was the variable, we wanted to hold mass and amplitude constant. Now you now know that amplitude had no effect on the period. But you know from day 2 that mass does. So the specific value of mass that you chose, or that we chose for you, did indeed affect the period. If you would have chosen a different value, you'd still get the same basic relationship that we're about to discover, but you would get a different, some different numbers coming out of it. But this amplitude, based off day 3, where we set this actually was irrelevant, because amplitude would have no effect, and it has no effect on this period here. And this is the data. And contrary to the previous experiment, it is clear that changing the spring constant does affect the period. As the spring constant increases, and you might think of that as a tighter or more forceful spring, as the spring gets tighter, the period reduces. In other words, a tighter spring contributes to a faster oscillation. Going through the curve fits here, there were a few options that seemed close to the general trend. Clearly none of these up here. However, you could go and check the linear and see that that's just going to be a really sort of poor fit of the data. and it doesn't really explain why there's this intercept. And I always think about the physical meaning of the intercepts when I'm seeing if a math model makes sense. When the spring constant is 0, in other words, infinitely loose spring, the period is still 1 second, and that doesn't make sense to me. So I'm almost looking for something that's going to, approach infinity as it gets smaller and smaller. Inverse does that, but this is a bad fit of the data and suggests, something else might be a better fit. Inverse squared, and then inverse square root. Now that looks like a great fit of the data. We don't put any statistical methods on here to see how good of a fit, but it's a very good fit. Other things that came up were an exponential decay. The exponential decay actually gets closest to sort of fitting all the data, but if we were to take some points in here, we'd find that the actual data was far higher on this list than this model would predict. So inverse square root is a much better model here, and we have this particular graph fit. So there's the math model. What does it mean? Well, we know what this means. We've got over x to the 0.5. Now, we have to keep in mind this is not y and this is not x. Y is a placeholder for period, and x is the general placeholder for spring constant here. Just a quick review, though. 1 divided by x to the 0.5 would be 1 over the square root. That's why it's called an inverse square root. So this math model here is really period equals 2.8, which I've just rounded off, divided by the square root of k. Another way to say that would be period equals 2.8 times 1 over square root of k. And in an inverse square relationship, we might say the period is proportional to 1 over the square root of k, and that's exactly what that statement says. Now, we don't do a lot of analysis with this. We don't do a lot of math problems with this particular relationship, and you really won't see any that problems in which we ask you to specifically just plug something in for that. So, but that is the relationship there. One thing I think you should know is that as we do increase k, it being in the denominator here, the period will go down. Even though it's the square root, increasing k will decrease the period. Just summarizing the entire set of results for the days, just going to talk through that real quick. Things we learned: period is the time to complete one oscillation, and on day 1 or day 2, or day 1, in that first time we took data, we found that in an oscillation the period stays constant. As long as we have an oscillation going, we don't see the period lengthen or contract. Day 2 told us that the period does increase with mass, but it's not linear, and that relationship was to the square root of m. So period was proportional to the square root of m. In our experiment, we found that the period was 0.051 times square root m. Period is not affected by amplitude. This is a surprising, counterintuitive, but correct conclusion. The amplitude does not affect the period. And then finally, on day 4, we found that the period decreases with the spring constant. But it's not linear, nor is it straight inverse. We found that the period is an inverse square relationship with spring constant. It's proportional to 1 over square root of k. In our experiment, we found that the period was 2.8 divided by the square root of k. Certainly any problem that asks you to use this math model and you just plug k in here to find the period, though we, like I said, rarely ask you to do that. Now this is really fun. I went ahead and looked up simple harmonic motion on Wikipedia, and I'm sure a few of you have looked at other resources. Okay, like 2 of you. But and it takes you through what the simple harmonic motion is. And there's some cool stuff here. Oh, and there's the restoring force, and it talks about that. But now there's quite a bit of math. And then look at down here, mass on a spring, simple system, and they tell us that the mass attached to a spring with constant k gives this relationship. And so this is actually the relationship for a mass on a spring. And I'm going to go back to the slideshow and show how this relationship here gives us everything we just discovered. So here's that relationship again, and this is just saying that the period is equal to 2 pi times square root of m over k. So anytime we wanted to find the period that would be reproduced if we hung a mass m on a spring of constant k, we could go ahead and plug in those values and find that. And this shows everything we already discovered, that up here in the numerator, the period would be proportional to square root m. Down there in the denominator, the period is proportional to 1 over the square root of k. And important to see what is missing from the equation. Amplitude is not in the equation. The two things that determine the period of a mass on a spring are the mass and the spring constant. And this is really about how tightly or how forceful the spring is. More forceful, less period. This is about how tough the mass is to move. If the mass is tougher to move, greater mass increases the period. Okay, and we could talk about what happens kind of when we change both of these. But this is the relationship we've really been working towards, and we don't really use this a lot. So, but this is the fundamental relationship that describes the relationship between these variables here. What we frequently will do, we'll just give you a math model, and you'll see this in the problems here. We'll give you a math model that just relates period to square root of m. And so you'll see that. But what that's basically done is combined these terms together once you decided to hold k constant. I hope you enjoyed this. Good luck with the problems.